Hello and welcome to TidyX episode 174, TidyX screencast, where we go through and explain how our code works. My name's Ellis Hughes.
Yeah, my name's Patrick Ward. Thanks for checking in with us at TidyX. As always, be sure to like and subscribe on the YouTube channel. Drop us questions, comments down below, etc. We do have a Patreon page if you enjoy the show and you'd like to contribute. We are very grateful for anything that you'd like to give. That said, episode 174, we're still doing our 20 minutes of insert X, whatever thing you wanted to learn. And we're still working with predicting MLB Pitching Hall of Fame um, uh, pitching MLB predicting MLB pitching Hall of Famers, and we've done a logistic regression, we've done a Bayesian logistic regression, and today we are going to do a neural network. So all of the processing stuff is in episode 172. So if you want to see how we got to the final data set, episode 172 is where you can do that.
Link
So
above.
we will a link above, yep. We will just jump right into getting ready for this neural network. Here we go.
Yeah, let's do it. So yeah, AI is definitely the hotness right now with OpenAI and all the LLM type stuff that's going on. But sometimes people don't actually know what is an AI model, how do you build that up? How do you maybe do that in R? I mean, probably not going to do an LLM in R realistically, but how could you make your own model to solve your own problems and build that up? So I thought this would be kind of a fun thing to do for us. So the two libraries that we're going to use today are library TensorFlow and the library Keras. Um, there's some setup involved because you're going to need to set up your Python environments and whatnot, and potentially download some software from NVIDIA so you can run CUDA. So there's wonderful instructions on tensorflow.rstudio.com that will get you all the information you need and really get you going. You don't need a GPU, I believe, to get the basic training going, but if you can set it up with CUDA, it runs significantly faster. Um, so let's load those up and let's get going. All right, we've got our data set. We can just go, right? Like we don't need to do anything else. We can just throw it in the AI model and it just works.
No, we got to sort out what to do with NAs, either get rid of rows with NAs, do a list-wise deletion, or do some sort of imputation. And then we need to get some level of standardizers, mean and standard deviation of the population that we're interested in, because everything inside of the neural network needs to be scaled so that the values are seen on their own or on their same on the same scale. So for example, something like batting average would be on a scale of 0.25 is the mean, whereas something like home runs is a pure count. And so we have to scale to standardizers.
Yeah, like here, like the IP outs is 3,000.
Thousands, yeah.
And meanwhile, wins and losses are like in the 60s. Yeah, as he said, batting average is in the points. So there's just widely scaled, and the neural network potentially could handle that, but it's a lot easier and it's going to train a lot faster based on what I've seen if you just scale it, right?
This is true for most machine learning models and for a lot of Bayesian models and mixed models. Scaling the values onto the same scale help the models, Bayesian models, mixed models, machine learning models, help them converge a lot faster as well.
Yeah. So let's do this. So we're going to use our training set of data, not our test, our training set. So this is the data that we're going to be building our model off of, and we're going to figure out what is the mean and standard deviation for every one of the values that we are going to be putting into our model. So we're going to take the pitchers eligible career stats Hall of Fame Sands 2018 final, which are the people that we officially know whether they will or will not go into the Hall of Fame for every pitcher post 1970 up until 2018. We're going to select wins through GIDP, convert that into a list, and we're going to then map across all of them and take the mean and standard deviation for every single one of those values there. So we get scale ref values, which then gives us a list of lists and then gives us a mean and standard deviation for every record there. The reason we do that is we're going to be creating a function that we're going to apply across all the columns going forward to do the scaling and then some replacing of NAs for us. And that's this function scale and replace NA. It's going to take in a vector that we're only going to be using this function inside of a mutate. So I'm taking and making an assumption here and calling substitute on x, which is going to give us the representation of the column that's going to be passed. And I'm going to call as character on that. And that way I can get the name of the column being passed to scale and replace NA, and I set that to xcall. By doing that, I'm able to pull out the mean and standard deviation that we just calculated up here, set that as x scales, and then do z-score normalization, right? So subtract the mean and divide by standard deviation to get to scaled x. But then we also need to handle, and I chose to do this all in one function just because it's a little bit simpler for my brain, and that way we don't have to apply multiple functions downstream to check to see if there's any NA values that exist in that vector, and if they do, replace those with negative 99999. And the reason we're doing that is we don't want to remove information from, like, our data set's already relatively small, right? So we don't want to be throwing away data just because. So I figured what I've understood about these models is if we throw a negative value that's totally outside the range of what we'd expect, the model should be able to learn that those are a nonsensical value and basically remove them. Now, I'm not an ML expert at all. I've kind of putzed around with things and played around with them. And these are things that I've heard from people. So if you know any better and work with ML stuff and know that that's not true, leave a comment down below and tell me how you'd handle this. How do you handle NA values in your ML models so that you aren't just throwing away potential data? So now we've got our scaling functions prepared. And basically all we're going to do here is we're going to take every single one of the data sets that we plan on using. We're going to then select or remove final season and then mutate across wins to GIDP and just scale all of them. So we can apply that to all three of them. The same exact code gets applied. But now we also need to convert them into a matrix or a simple array where every row represents a sample and every column represents a variable that we're going to be training our model on, because TensorFlow models expect an array. There's a lot more in-depth information explaining the structures. If you're going from here, we're just doing rows representing pictures and columns representing stats, but you can do pictures, you can do videos, you can do much more complicated and much larger data sets with n-dimensional arrays. Read the TensorFlow with R book by Francis Chalet and JJ Allaire if you want to learn more about how that works. When I first read that, my mind just was like, what? I didn't even, how does that work? So definitely look into that more if this is sounding interesting to you. But what we're going to do here is we're going to take that scaled data set there. We're going to then, again, remove player ID and inducted and convert that into a matrix. That's all we're doing in this situation here. But we also need our source of truth as a matrix. So we're going to take that same data set, select inducted, convert it into a numeric 1 or 0, and again, turn it into a matrix. So you can take a quick head of this first one. This is the data set we're going to be passing in. And then this is the source of truth or ground truth. And again, it's just a matrix where every row represents the output, every column represents a different predictor, because you can also technically predict multiple outputs. So now we can go and train our AI model. Now our data set's prepared. Patrick, how do we define our model?
So first, we're just going to, which is a little bit different, I guess, for neural networks, is you have to define the model before you can sort of run things. I guess this is sort of similar to how tidy models works. You have to define all of the things that you want to happen before you actually fit the model. So we're going to define a basic convolutional neural network. We're going to make this simple with one hidden layer. Obviously, deep learning is just like many hidden layers. So throwing in a whole bunch of different hidden layers, and you can use different activations, and you can use a different number of nodes within those layers. But in this case, we're going to specify that we want a Keras model. The input shape is specific to the number of independent or predictor variables that we have. So we have 23 predictor variables, and we're going to make sure that Keras knows that that's the input shape that we're going to feed to it, so it can do the magic that it does under the hood. Like I said, we're going to just drop in this single layer. It's a single layer model, so it's got one hidden layer that's going to sit between the model inputs and the model output. And this layer is going to have 64 nodes. Again, you can try different nodes. You could try different layers. I would read Francis Cholet's book on deep learning. I've never read the R one. I actually, full transparency, sorry, R people, I always build these in Python, not in R, but same concepts. So we have 64 nodes. We have this single hidden layer. We're setting our activation unit to be a rectified linear unit. This is a very common activation unit within hidden layers. And basically all it's doing is it's checking the output and saying, take the max of either 0 or X. So with X, whatever output value from that hidden layer gets chunked out, if it's greater than 0, we're going to accept that and move on, okay? And then we have an output layer. So this is the final layer of the model, and it's basically saying, hey, we want an output, and we want it to be a sigmoid function, which basically means we're looking for values that can only be between 0 and 1. So they have to be bounded between 0 and 1, because the outcome here is going to be probabilistic. What's the probability that pitcher X makes it into the Hall of Fame?
Mm-hmm.
So once we've specified that model, we can then tell the TensorFlow model what kind of we compile the model before we fit it. So we compile this model. We're going to use a loss function, which is basically helping the during the epochs that we set. It's going to help the model learn and get smarter over time. So this loss function that it's trying to minimize is going to be mean squared error. The atom optimizer is one of the most common optimizers that people use in neural networks. And then the metric that we're interested in, the output metric that we're interested in, is model accuracy. Like, as the model goes through its epochs, can it get smarter and become more accurate at identifying the pattern of data that sees players more highly making the Hall of Fame?
Mm-hmm. Yeah, so these two options here are really what's training the model. This
Mhm.
metric here is something that it's going to just keep track of so that we can see as it gets trained what is the accuracy of our model over time. And it's just, you don't need to put that in there for the model to train. You could just do this.
And
But I like to see the accuracy. It was helpful for me as I was creating this.
it's also helpful to look at these things to identify any potential overfitting. So once the model
Exactly.
starts to fit too much to the data.
Yeah.
Yep.
So now that we have our model, we can fit it finally.
Yay.
13 minutes into the episode, we can finally fit our model. So what it takes is a couple different arguments. So the function fit takes first the model. So we're just going to pipe that in. It takes the training set of the input training set. So again, the scaled stats. Then it takes the prediction matrix, and this is our scaled results. Well, technically it's not scaled, it's still all between 1 and 0. Then we're going to specify the number of epochs, so the number of times it's going to go over a training set as it's learning. So we're going to say, hey, go over a training set 100 times. You can set that to be 1,000. I'm sure some of these bigger models have billions or hundreds of thousands of epochs as they're training over it. And the next thing I'm going to do is set sample weight. So sample weight is what I really want it to do is very accurately predict who's going to get in. I care less about it accurately predicting who's going to be out, because the odds that somebody's not going to get in are very, very high. The odds that somebody are going to, or did I switch that up? The odds that
No,
somebody
that,
is not going to
yeah.
get in are very high. The odds that somebody will get in are very low.
You
So
want a model that's more sensitive to that.
yeah, I'd
Yeah.
rather it predict more people than less people. Otherwise, you're going to have a model that's just going to go, well, nobody's going to get in. Cool. Just predict 0 and your accuracy is like 97% accurate
Yeah, but your
because
model's
only,
not useful.
and
Right.
yeah, it's not helpful. So I'm
Right.
really strongly weighting it. I'm saying weight the people that got in at 200 and weight the people that didn't get in at 1. So it's a very strong weighting in this situation. I was just playing around with this weighting. Again, if you're an ML expert, please leave a comment down below of how you deal with the sparse results in your ML models.
Hmm.
Do you add additional records, or we've talked about this in the past? And then finally, I'm going to set verbosity to true, and this means now when I click run and it's going through, it's going to create this model or show me how the model's performing on the right hand side here. It's
Hmm.
going to also then print into my console every epoch that it's gone through and the loss that it has and the accuracy that it has. And so again, we've only set it to be 100 epochs, so it ran all those. It split it into 18 different sets, and that is based on the, I believe there's an argument for batch size,
Yeah, batch size.
and
Yep.
then it also printed out the loss and accuracy here. And so as you can see, it got progressively better over time. It's at, I think it finished at 96 point, yeah, 96.965. There we go. English is hard sometimes. And a
Yeah.
loss of 1.4. So it's just kind of nice to, like, you can set that to be false and it runs faster because it's not having to spend a moment printing all these things out. But in our case here, I wanted to see it all as it was training, and you can see that there's no point where it really starts losing accuracy over time. So we could potentially continue to do more epics, and we could just press fit again, and it'll continue from this point here and continue to fit even more. So now that we've got
Hmm.
this, we can actually inspect our model results and go, how did it perform? How is our AI model here smarter than Bayes? So the way you do that, well, maybe not smarter than Bayes, but the way that you inspect to see how the results is you use the predict function, as we've seen many times here on TidyX here. We pass the model that we predicted, as well as here is the training data that we trained on. So we pass that in, and it will give us then again, a matrix of all the predictions. We can then take the final data set, mutate a column called pred based on the Hall of Fame and left join people. And now let's look at the top 20 people that our model says should be in the Hall of Fame based on the training set. And if you look at that, the person that it says absolutely 100% should be in is Roger Clemens. And then Greg Maddox, John Schmaltz, Dennis Eckersley, and then here's Randy Johnson down here. So it is accurately predicting for a good chunk of the people that we said should get in. It said yes, and they will get
Hmm.
in. And there's a couple other people that, based on the statistics, it thinks should have gotten in, like Kurt Schilling and Roger Clemens, that for whatever reason outside of statistics, based on our model, didn't get in. And now these two folks, I believe, were from the PED era. So I think they might have been accused of that in the past. I don't know if there was any evidence around that, but because this is a vote and not just based on raw stats, they didn't get it. But that's not why we built this model, because it was trained on this. It should be good on this. Oh, I guess we can also look at a histogram of the actual predictions. Again, most people are down in the lower probability with a handful of people up close to 1.
Hmm.
And then we've got some other stuff looking at who got in and those predictions. So we've got a couple people here that did get in that our model doesn't think should have gotten in, and there's a 0% chance that they think that these people should have gotten in for whatever reason. So that might be a reason to inspect your model, as well as looking at the top people or the people that it thinks should have gotten in that didn't. So Jeff Reardon, Rick
Hmm.
Aguilera, Frank, Kevin.
Hmm.
Again, look into that. You can look into that and start to suss out your model and understand what's going on. How might an average person, average pitcher, what's the probability of them getting in? So you take the scale data sets, average across all of them, turn it into a matrix and predict. And if you're average, sorry, our model says you're not getting in.
Mm-hmm.
But what about the 2018 class, the people that or the people that are just now eligible to get in? So again, we take their data set, we select wins through GIDP, turn it to a matrix and predict it, drop that in, add people, select their player ID, their names, and their prediction, and we're going to arrange it by descending order.
Mm-hmm.
And Bartolo Colon has a 40% chance per our model to get
Great. Former Cleveland Guardian.
in. we did not seed this so that it would be like that. That
No.
is just what our model says. And then finally, for the group of people that we're still waiting to find out their final results. Again, select wins through GIDP, turn it into a matrix, call predict, add it into the pred column, arrange by descending, and it says Tim Hudson has a 73% chance of getting in, or should have a 73% chance of getting in. Francisco Rodriguez, Tom Gordon, all should be able to get in.
Mm-hmm.
Here I'm going to grab the ID of the top person. So I'm going to say which is the maximum of the predictions. Grab that player ID, so Tom Hudson, and look at them. This person only got 21 votes in 2021 and then got even less votes in 2022. So don't know how they did this past year, but our model says they should based on their stats. Don't know if there's anything else holding them back. And then finally, as a Mariners fans, Seattle Mariners fans, let's look at Felix like we did last week. Pull out his player ID, filter to grab his stats, and then do a. So we got his pitching stats. We're going to mutate across all of them and scale and replace his values, because remember we hadn't done that yet. He's not in the SANS 20 or in the 2018 data set. Convert it into a matrix and call prediction. Hey, our model says there's a 52% chance that Felix gets in. And as a Seattle person, I'm good with that. But that is wow, we almost hit 20 minutes too. Look at that. That is how you ask or train an AI model to predict pitchers getting in to the Hall of Fame in 20 minutes. Patrick, do you have any other comments?
No, that's pretty much yeah, that's pretty much it. If there's a different classification technique that you'd like to see, comment and say, hey, I'd love to see you do the same thing with, insert whatever favorite classification technique you have. And maybe we'll do that.
Maybe. All right, with that, I guess we're going to call it. As always, my name's Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
My name is Patrick Ward. You can find me on Twitter at OSPPatrick. At Tidy_explained is where we both are on X, not Twitter, sorry, on X. And the YouTube channel is the easiest way to get in touch with us. Like, subscribe, drop the questions, comments down below. We have a Patreon page if you'd like to donate to the show. Super appreciative of anything you'd like to give. That said, that's TidyX episode 174.
174. Thank
There
you
we
all
go.
so much, and keep on exploring your world.